Welcome to the lecture series of probability and random processes. Today we are going to discuss about discrete random variable. In the previous lecture video we have discussed what is a random variable. After that we have a type of random variables. One is discrete random variable and another one is a continuous random variable. Today we are going to discuss about discrete random variable. When we can say that a random variable is a discrete random variable. The definition is a discrete random variable is a random variable x whose possible values constitute finite set of values or countably infinite set of values. So, the possible values have only finite set of values or countably infinite set of values. It is very important. Then only we can say that a random variable is a discrete random variable. Example for this, when you are tossing a coin twice, getting number of tails or getting number of heads, all these things comes under discrete random variable. The next one is distribution function or cumulative distribution for a random variable. The distribution function of a random variable capital X defined in open interval minus infinity comma infinity is given by capital F of x is equal to P of x less than or equal to x, which is equal to P of set of all s such that x of s less than or equal to x. If this notation is denoted for distribution function. So, for the distribution function, the notation is capital F of x. Capital F of x is equal to probability of a random variable less than or equal to that value. So, this is the notation for distribution function or cumulative distribution. So, example, let the random variable capital X takes the values x1, x2, etc. up to xn with probabilities p1, p2, etc. pn, and let x1 less than x2 less than x3 etc. less than xn, then the distribution f of x is equal to p of x less than x1 equal to 0 such that minus infinity less than x less than 1. So, here what we are discussing means if I am having a random variable capital X whose values, here we have denote the general p of x less than or equal to x. The same manner if I am taking the probability random variable capital X, for that the values are x1 to xn, p of x less than or equal to x. Instead of this x takes the values x1 to xn with the probability p1, p2, etc. pn. With the same, at the same time, x1 is less than x2, x2 is less than x3 such that xn is also like that, x3 etc. xn minus 1 less than xn. Then the distribution function f of x is equal to, first we are taking the first value x1, p of x less than x1, because the definition of distribution is f of x is equal to p of x less than or equal to x. So, here the first value of the probability random variable is x1. So, according to the definition, first we will take the less than value p of x less than x1 equal to 0, because here we have take the values, that is capital X takes the values x1 to xn. Okay, there is no value less than x1. That is the reason why the probability of less than x1 is 0. So, this 0 takes in the interval minus infinity to x1. So, what is the next value? Next value is x1. So, the distribution function f of x is equal to p of x less than or equal to x1. So, less than or equal to x, no, general definition. Same manner p of x less than or equal to x1, first value, which is equal to, this less than or equal to x1 can be splitted as p of x less than x1 plus p of x equal to x1. Just now we have seen that p of x less than x1 value is 0. So, for the first one the value is 0 and p of x equal to x1, the probability is p1. x1 means the probability is p1. So, here it is p1. So, the final answer is p1. So, the distribution function is p1. Likewise, for the next value is x2. Corresponding to this x2, the probability is p2. So, the distribution function f of x is equal to p of x less than or equal to x2. So, this x2 less than or equal to x2 means, which is equal to p of x less than x1 plus p of x equal to x1 plus p of x equal to x2. This first value is 0 and the next one is p1, and for the second random, that is the second value, the probability is p2. So P2. So the final answer is P1 plus P2. Likewise, if I am taking P of x less than or equal to x3 means P of x less than x1, P of x equal to x1, P of x equal to x2 plus P of x equal to x3. That means the final answer is P1 plus P2 plus P3. Likewise, if you are going for the final value, that is the nth value, P of x less than or equal to xn, it is equal to P of x less than x1 plus P of x equal to x1 plus etc. plus P of x equal to xn. So obviously the final answer is P1 plus P2 plus etc. plus Pn, because the nth value, the probability is Pn. So which is equal to 1. We all very well know that probability of A plus probability of its complement is always equal to 1. So all the probability, adding all the values, the final answer should be 1. So the distribution function f of x is equal to P1 plus P2 plus etc. plus Pn, which is equal to 1. So this is the way we have to do the problem under the distribution function in discrete random variable. So the notation for distribution function or cumulative distribution is capital F of x, which is equal to P of x less than or equal to x. Okay, so we have to remember this notation. Now the next one under the discrete random variable, probability mass function or probability function, or simply this can be denoted as P.M.F, probability mass function. So P.M.F for only discrete random variable. Okay, let x be a one dimensional discrete random variable which takes the values x1, x2, etc. To each possible outcome x suffix I, we can associate a number Pi, that means probability, that is P of x equal to xi, which is equal to P of xi and which is equal to Pi, called the probability of xi. The numbers Pi equal to P of xi satisfies the following conditions. The first condition is P of xi greater than or equal to 0 for all I, sigma I equal to 1 to infinity, P of xi equal to 1. So these two conditions, P of xi greater than or equal to 0 for all I, summation I equal to 1 to infinity P of xi equal to 1. The function P of x satisfying the above two conditions is called the probability mass function or probability function. So what is the definition for probability mass function or P.M.F? The P.M.F means P of xi greater than or equal to 0 for all I and sigma I equal to 1 to infinity P of xi equal to 1. Then we can say that the probability P of x satisfying these two conditions, which is called it as probability mass function. So the probability mass function can be denoted as a set notation, that is set of xi comma Pi. This means the value is xi, corresponding probability is Pi. If I am taking the first value x1, corresponding probability is P1, x2 means P2. So we can denote as a set. So this set is called it as probability distribution of the random variable capital X. So the distribution function xi comma Pi can be displayed in the table form, that is x is equal to xi means the values of a random variable and P of x equal to xi equal to Pi, that is the probability values of the random variables. So first value is x1, x2, etc. xi, corresponding probability values P1, P2, etc. Pi. When we are adding all the values, it is equal to 1, that is the condition for P.M.F, that is probability mass function. So probability mass function, a very important condition is P of xi greater than or equal to 0 for all I and summation I equal to 1 to infinity P of xi equal to 1, satisfying these two conditions only for probability mass function. Okay. Now there are very important theorems under the discrete random variable. These two theorems are very important. What are that? The theorem 1 is if x1 and x2 are random variables and k is a constant, then kx1, that means the first random variable multiplied by the constant k, so that only we can get kx1. And the next one is x1 plus x2, x1 plus x2, x1 x2, k1 x1 plus k2 x2, comma x1 minus x2 are also random variables. This is the first theorem. So what is the theorem says? If we are having a random variables, that is x1, x2 or two random variables, k is a constant, means when you are multiplying the random variable with a constant, that value is also again a random variable, that is kx1 is also a random variable. Same manner, if I am taking k1 and k2, two constants, multiplying the first random variable with k1 and multiplying the second random variable with k2, adding these two, k1 x1 plus k2 x2 is also a random variable. Same manner, simply we are adding these two random variables x1 plus x2, that is also a random variable. Multiplying these two x1 x2, that is also a random variable, and subtracting these two x1 minus x2, that is also a random variable. Adding these two is also a random variable. That is what the theorem says. If x1 and x2 are random variables and k is a constant, then k x1, x1 plus x2, x1 x2, k1 x1 plus k2 x2 and x1 minus x2 are also random variables. Okay. Then the next theorem is a very important. Based on this only we are doing problems under discrete random variable. What is the theorem says 2? The theorem 2 says that if x is a random variable, f of x, that is the distribution, is the distribution function of capital X, then first condition 0 less than or equal to f of x less than or equal to 1. It's a very important thing, because if x is a random variable and capital F of x is a distribution function, means it takes values always 0 to 1. That is what the first condition says. If x is less than y, that means x is a random variable value and y is another value, then distribution function of x and distribution function of y is also less than or equal to, that is f of x is less than or equal to f of y. That is the second condition. And the third one is f of minus infinity, that means limit x tends to minus infinity, f of x equal to 0, f of infinity, that is plus infinity, okay, limit x tends to infinity, f of x is equal to 1. This is the distribution function condition we have discussed. Okay, and the last one is very important. P of x is equal to xi, this is equal to f of xi minus f of xi minus 1. This condition we used to do in the problems based on these conditions. Okay, so all the conditions are very important, especially the last one. For doing the problem under the discrete random variable, we are using the fifth condition very often. Okay, so these are the two important results under the discrete random variable. Okay, so based on the discrete random variable, we will do problem in the next lecture video. Okay, thank you for watching.